So the second thing is I had put up last time this overview of the Ford Fulkerson methodology, which is kind of what we've been working on for the last week and a half. And the Ford Fulkerson methodology for max flow is to start with a directed graph that has capacity on each edge, then repeatedly go and you're going to find paths from the source to the sink. So to start with, just find any old path from the source to the sink. And this could be, for example, depth first search. But you just search from A and go like wander arbitrarily or randomly through your graph and come up with like some path from your source to your sink. And then once you've done that, then you go and pump as much flow as possible along that particular path. So you look at like, on this one path that I found, what is the bottleneck on that one path? And then go and pump as much as possible until you hit that bottleneck capacity. And then we now repeat this loop where we construct the residual graph and we add backtracking edges wherever we have flow. We go and have a backwards capacity on these new backtracking edges that are equal to whatever the forward flow is. And then similarly, we have residual numbers on the forward edges. So the forward edges get, this is not the current flow on the edge. This is the capacity minus current flow, right? Your residual capacity is your capacity minus the current flow. And in the backwards direction, you have the backwards capacity is the current flow. So in particular, it's always going to be the case that you either have a non-zero number going forward or you have a non-zero number going backwards. It's always possible either to pump more flow through the edge or it's possible to like backtrack. And by backtrack, I mean you had planned on sending flow on this edge, but you realized that it wasn't a good idea. So you go and pull some of that flow back. Then once we have the residual graph, we find an augmenting path in the residual graph that doesn't use any zero capacity edges. So it might use some forward edges, it might use some backtracking edges, but we find some path that allows us to pump more flow from A to B. And then we go and update the current flow by sending as much as possible along this augmenting path. And when we can no longer find an augmenting path in the residual graph, then we're done. And we declare victory, and we have found the maximum amount of flow that we can send. So this is the high-level approach, and this is review from last time. But I wanted to take a minute here to go and talk a little bit about the runtime. So if I talk a little bit about the runtime of Ford Fulkerson. So the runtime of Ford Fulkerson is going to be, okay, there's this startup stuff. How long does it take to search and find a path in a graph? There's the like find a path. So I believe that we can find a path in order E time. I think if you go and look at every edge, if you consider every edge, I believe that, I believe that depth first search is going to go, or breadth first search, I believe is going to be order E time. If it's not order E time and I'm misremembering, somebody should go and type it into the chat. but you need to find a path, and then there's this loop. And inside the loop, you basically need to, finding a path is the, or I guess there's the like update residual graph. So updating the residual graph is going to involve going and looking at every edge and going and changing the numbers, the like brown numbers and the red numbers on every graph. And then we need to find an augmenting path, which should also be O of E time, because this is like a breadth first search, or a depth first search, or whatever you want. So basically, Ford Fulkerson is doing a bunch of things that are like on the order of the number of edges in the graph. And the real key question is, how many times through the loop? How many times through the loop? And the number of times through the loop is, I mean, this is a little bit tricky. I'm going to pause just a moment. I'll be right back. Okay, so the number of times through this loop, well, every time through the loop, we increase the amount of flow that we are sending by at least 1 unit. So every time through the loop, we get to send, let's see, every time through the loop, we get to send more flow, right? That's the idea behind this algorithm, is we keep finding clever ways to send more flow through our network. And because of that, well, maybe we get lucky and we find a path that allows us to send like 100 units of flow at once along a path. But in the worst case, we only get to send 1 unit of flow each time we find a new path. So then we need to run the loop. We need to run the loop like order of, right? However much the max flow is, that's how many times we need to run the loop. So for example, let's go.
How many times was it? Oh, max flow times.
Yeah. So if the max flow were 17, we might have to run the loop. 17 times. So this is actually a weird runtime where the runtime, the number of times through the loop, is based on what the answer is that we're finding. So the bigger the answer that we find, the longer it might take to find it. So also we can upper bound this. So we can upper bound this like maybe there are better upper bounds, but a loose upper bound is order of the like total capacity in the graph. So, or actually, let's say the the total capacity. So so the total capacity in the graph is an upper bound on the max flow. The max flow can't possibly be bigger than the sum of all the edge capacities. And in fact, the max flow can't possibly be bigger than the sum of the capacity out of A. So right, every unit of flow needs to leave A. Also, every unit of flow needs to come into B. So what I'm trying to say here is, if we look at a graph, when we find a graph and we're thinking about running Ford Fulkerson on this graph, before we run Ford Fulkerson, we don't know what the max flow is. So we don't know how long it's going to take until after we've run it, because again, if we knew the max flow, we wouldn't have to run the algorithm, right? So this is the if we knew the max flow, we wouldn't run the algorithm. So it's useful to be able to get a rough guess of the runtime without actually having access to the max flow. And so this is where you might do something like look at the sum of the capacity out of A. That's something that is really easy to figure out just by looking at the graph. And so that's a way to provide a loose upper bound on the amount of flow that could possibly get from A to B. Yeah. So the other thing that I'm going to just toss out here, and I think if we have time at the end of the course, I'm going to come back to this, but just FYI, we call these algorithms that depend on how big the numbers are, how big the edge weights capacities are as in general, polynomial time graph algorithms are things that we've been looking at, things that are like order of like E squared or order of like V times E. So these are like polynomials in the number of what this is like polynomials polynomials using the number of edges and vertices. So so polynomial is just like something squared, something to the third, something to the first power. Those are like polynomials. And yeah, so in general, when we're talking about graph algorithms, most of our algorithms are like a polynomial in the number of edges and the number of vertices. And these weird algorithms like Ford Fulkerson, where how big the numbers are on the edges really matter. So, right, one thing to keep in mind is if you think back to like Dijkstra's algorithm, the number of times you needed to like run through the loop, the number of the runtime of your algorithm didn't care whether or not the numbers were like in the thousands or if the numbers were like 1 or 2, because all you were doing was just like taking these numbers and like adding them together and copying them down somewhere. You were never like looping where the number of times through the loop depended on how big the numbers were. So anyway, this is not super important. This is like a random side note. But we might be able to get back to this at the very end of the term. I don't know exactly how much time we're going to have. So in any case, this is Ford Fulkerson and the runtime for Ford Fulkerson. And I'm going to check in the chat here to see if there are any questions about, let's see. So, okay. So let's see.
Yeah, what is the actual final runtime for this?
So the, okay, 1 second. Oh, so I'm sorry. So the final, I forgot to multiply. Okay. So the final runtime of the algorithm is O of E. So the reason we have this E is because every time through the loop, we need to go and update all of the edges and then do a breadth first search. So it's E times, this is, thank you very much for reminding me that I actually have to do the multiplication. O of E times the sum upper bound on the max flow. So again, you probably, if you look at a graph, you probably don't immediately know the max flow. So usually we use something like add up all the numbers coming out of A and use that in your big O, because again, big O is just an upper bound. So it's going to be E times some upper bound on the max flow. Okay. Sorry about that. Wait, is, so, that, so this is, okay, so the, you might have seen in your textbook, so if you assume that all of the capacity, wait, is this, did I forget a factor of V here somewhere? Is finding a path V times E for breadth first search? My apologies here. So if I assume that all of the capacity numbers are small, if I assume that all of the capacity numbers are small, like less than a constant, then you get the like Edmonds Karp, which is O of is what was the Edmonds Karp bound was where is the V coming from here? So so what the Edmonds Karp explanation in the book is doing is it's somewhere, I seem to have lost, oops, somewhere I lost a factor of V. Shouldn't I have a V somewhere? But I can't, is this like V times E? Oh, V is the size of the longest path. Yeah, okay. Yeah. So this is the, is that the,
Is Edmund's carp something that really has to be on our radar, or is this just like a side note?
So Edmund's carp is just it doesn't need to be on your radar. So this is so Edmund's carp is just, it's in your book, which is the reason I bring it up. So Edmund's carp said, hey, if your capacity numbers are small and you use depth first search to find your path, then it's going to be O of E times V. So this is it's a theorem due to Edmonds and Karp. It doesn't need to be on your radar. Okay, so find an augmenting path. Okay, so yeah, basically, if the numbers on your graph are really big, like in particular, if the numbers on your graph are like larger than the number of vertexes or edges in your graph, if they're like, if the numbers on your edges are not like some small constant, but are something that is like on the order of the size of your data set, that or heaven forbid even worse, then in that case, then this upper bound on the max flow is going to be really, really big. But what Edmonds and Karp are saying in their theorem is that as long as the numbers that we write on our graph are really small numbers, like less than a constant, that the numbers on the graph are not something that is growing asymptotically, then we don't, then in that case, we get a more simple formula for the max flow bound. So, okay. I apologize. I think that, breadth first search is V plus E. Yeah, so there's, okay. There's something a little bit wrong here. I will try to figure it out. But the most important thing, try to pull back here for a second. Yeah, the most important thing that I want you to walk away with, even if I'm a little bit confused, is that, so there's this basic methodology that the number of times that you need to send flow, the number of times that you need to send flow, the number of times that you need to go through your main loop depends on what the max flow is. And so if the numbers on your graph are small, then the amount of the max flow is going to be like about the same order of magnitude as the number of edges in your graph. But if the numbers on your graph are big, then this algorithm slows down a lot. That was the only point I was trying to make. So anyway, I apologize for getting hung up in the details of these runtime analysis. I feel like, I want you to get like the big picture thinking about runtime, but I like mess up the details all of the time, and I apologize for that. And it's like, obviously it gets worse when I'm trying to do this remotely.